So again, as I was emphasizing, we express our concentrations here in leaching in terms of A and C only in the denominator. We don't include in the denominator the inert insoluble solid B. So whatever is in the numerator, that's the particular component that we wish to account for in terms of its concentration, but always the denominator is only in terms of the solute A and the solvent C. We don't include B in there. Even in the manner we express the concentration N, and that is your inert insoluble solid. Now, for the feed, your feed then will have an N equal to kilograms of B, that's your inert insoluble solid B, and your solute A. Now, most of the time, our feed does not contain the solvent itself. It's ironic if it will contain the solvent itself. So it's only A present. So that is why your N for the feed is simply kilogram B over kilogram A. It follows then that the concentration of your feed would be YA being equal to 1. And that is kilogram of A over kilogram of A, which is 1. Now, for the entering solvent, this is most of the time, it's free of the inert insoluble solid B. So then N will be a 0. And then it's also free of the solute A. The reason why it needs to dissolve A is because it's pure solvent. So we don't have A in our solvent. So you have kilogram A being 0, so your concentration for it would be 0. So this too is always true in the case of feed and solvent in terms of the N and the concentration of both phases. Now, this is not taken from John Publius, nor this is taken from McCabe, and this is the first time I'm using it in your case. Because if you have your copies of the book by John Publius and McCabe, you will notice that in leaching, most of the sample problems are all treated with graphical approach. Now, there's not a problem in there which is being solved purely using analytical process. Now, in the board exam, you'll be using equations that are not relying heavily on procedures dependent on graphs, or shall I say graphical approach. So this one was taken from Paulson. If you're given a pure solvent that is 100% C, you're able in this particular equation to account for the concentration of the solute in the bulk of the solution at time t, meaning you are able to compute or determine the amount of A present in the bulk solution at any particular time t. Now, what do you have in this formula? The formula is dependent on C sub S, which is the concentration of the saturated solution in contact with the particles. This is normally given by the problem, the concentration of the saturated solution, whereas C is just the concentration of the solution at any particular time. So in this formula, you have the K prime, which is the diffusion coefficient. It's a constant. The A, which is the area of the solid-liquid interface. This is also a fixed. It should not be varying. The B is the effective thickness of the liquid film surrounding the particles. So we view in the case of leaching that your individual particles are being surrounded by this liquid film. The thickness of that liquid film is letter B. Then we have the V as the volume of the solution. I was not able to include it here. It's the volume of the solution, and of course T is the time. You have to take note, however, class, that when you use this particular formula, your solvent has to be pure, and this is only applicable for a single stage leaching. So the formula is only applicable again for single stage leaching. The constants that you have in this formula are K prime, A, and B. This could be provided for by the problem, or this could be determined as one whole thing depending on the requirement of the problem. So to illustrate the use of this particular formula and without having to rely on graphical approach for now, let's have this sample problem taken also from Paulson. So here we are determining the leaching time the leaching time based on this particular formula. So in a pilot scale test using a vessel which is 1 cubic meter in volume, a solute was leached from an inert solid and the water was 75% saturated with the solute, of course, in a span of 100 seconds. So take note, a solute was leached from an inert solid and the water was 75% saturated in 100 seconds. If in full-scale unit, so this one is pilot scale. Now, if in a full-scale unit, we now have 500 kilograms of available inert solid containing, just like as before, 28% by mass of water-soluble component. This one is viewed to be your solute A. It is agitated with 100 cubic meter of water so that your water-soluble component gets to be leached out from this matrix of inner solid. How long will it take for all the solute to dissolve, assuming conditions are equivalent? So, assuming the same conditions as the pilot scale vessel, meaning we will use the information we have in the pilot scale test in this full scale unit. Now, water is said to be saturated in both of these conditions with the solute at a concentration of 2.5 kilograms per meter. Now, how do you view this water being saturated with a solute at a concentration of 2.5 kilograms per liter? At this particular concentration class, meaning for every 1 cubic meter of water, if there has already or if it contains already 2.5 kilograms of solute A, it will not anymore be able to dissolve more A because it's said to be saturated. Or shall we say this is already the maximum amount of A per unit volume of solvent that was used in extracting A to have in your solution. So your solution should have this maximum concentration. So we need to write down the given information that the problem gives us. So I will stop sharing here and class. Go to use of the board. Okay, class. So that was our problem. I will just go back to the problem later. So we will write down what we have in terms of the given. Okay, I'll go to the PowerPoint. I will not show it to you anymore so that we can save time. So we'll have two scenarios here. We have the pilot scale and we have the full scale here. Okay, two conditions. In the pilot scale, it says that you are given a 1 cubic meter volume of vessel which will house a solute and it will be saturated with UC to 75% saturation in 100 seconds. So I'll read the statement. In a pilot scale test using a vessel of 1 cubic meter in volume, a solute was leached from an inert solid and the water was 75% saturated in 100 seconds. So in 100 seconds. So at T equal to 100 seconds, C is equal to 0.75%. of saturation concentration. Okay? I will read again so you will understand. A pilot scale test is using a vessel 1 cubic meter in volume. A solute was leached from an inert solid and the water was 75% saturated in 100 seconds. So it's 75% saturated in 100 seconds. So our volume, I missed to write that down, in this scenario is 100, no, it's one lang only. It's 1 cubic meter. So this is what we know for our pilot scale. For the full scale, it says here that you have 500 kilograms of inert solids. So we have here mass, 500 kilograms solids. Okay. Says here it contains 28% by mass water soluble component. So we can write here that your A, your solute, which is water soluble, is 0.28 of the entire mass of this solid. 0.28, why did I place M there? 0.28, right, of M. Why did I erase? So I referred into it at M, so this would be M. Okay? Now the volume that was used here is, it's agitated with 100 cubic meter of water. So the volume used here is 100 cubic meter of water. Both conditions are using pure water as the solvent. So you are required, in this case, the time. The time to, says here, I'll read again. How long will it take for the solute to dissolve in this condition? You are provided with 500 kilograms of solid, which contains 28% of A, and you are going to use 100 cubic meter of water. How long will the leaching process proceed in this case? Okay? So we have water is saturated with a solute concentration of 2.5 kilograms per second. So I will write that your C sub S, by the way, in here, which I was not able to write, in both conditions is 2.5 kilograms per cubic meter. By the way, there's a typo error here in the problem. This should be only your, in the pilot scale, your 1 cubic meter equipment or volume of solution will be having 75% of the solute, or that should be 75, it becomes 75% saturated in just not 100 seconds, but rather only uh, 10 seconds. We'll only have this 10 seconds to change this. So this would be 10 seconds here. Okay. So now we go to our solution. These are all the information that we can use. We go to our solution. So we need to write down the formula to be guided. So C is equal to C sub S. What's the rest of that formula? I will just 1 minus E negative KBT, oh, KA over BVT. So this should be A. KA over BV, then we have T. So this is our formula. So we'll use first the pilot data. In the pilot data, it says that if we go to that particular slide, your C is becoming 75% of the saturated value in 10 seconds. So what do? We use this particular condition, this one, these three, volume, T, and C, in order to find this constant K, A, and small letter B. Because we do not know this, the problem does not give us these constants, the diffusion coefficient, the area, and the thickness of the liquid film surrounding every solid particle. So we need to determine this particular constant. So we need to determine the C first. So your C is 2.5 kilograms. This is your saturated value, and this is reaching 75% of its value at the time given, which is 10 seconds. So if you will determine the C, this would be 1.875 kilograms per cubic meter. Then you go back to that equation and substitute. So you have 1.875. Actually, pwede naman lang hindi. Dili. This is equal to C sub S, which is 2.5. And we have this 1 minus E raised to negative. So we have K, A. The time that we will use is 10 seconds. And the volume here is 1 cubic meter. And we do not know this B. And by the way, this has prime. Okay, diffusion coefficient. So from here, we'll be able to determine the constants group K prime A divided by B. So 1.875 divided by 2.5, of course, that would be 0.75 minus 1 divided by, or that would be, we take the ln of our answer and then we divide it by 10. So our K prime A over B is 0.1386. 0.1386. So this is for the pilot data. The same system we'll be using, only that we're using a smaller amount in the pilot scale data. So now we go full scale, and we will be using a formula which has already the constant. So I will have E, and then this Ka over B we will write as negative point. This Ka over B we will write as negative 0.1386 here. So 1386T over the volume. The volume is not included in the constant because in full scale, our volume is expected to be different than the pilot scale data. This would be bigger, whereas in the pilot scale, of course, we expect it to be smaller. So now here, we need to determine the C in the uh, full scale design. How do we determine the C? So your C is said to be concentration is mass over volume. Now, if we go back to the given, it says that we have 500 kilogram solids containing this much 28% of solute. So we'll have here 500 times 0.28. This numerator now will represent kilogram of the solid A, divided by the amount of solution, in this case, which is 100. So you'll have here 100 cubic meter. So you'll have a concentration here of, we'll cancel the two zeros, you will have 5 times 0.28. In that case, you will have a 1.4. So this is kilogram per cubic meter. Now you can go back here and determine the time. So you'll have a 1.4 being equal to 2.5, we have 1 minus e raised to negative 0.1386. We don't know the time. We divide this by 100 because our volume is 100. So you will have a time value here of 1.4 divided by 2.5. Subtract 1 from that. We take the ln. We multiply by 100 and we divide by 0.1386. That should be, for the time, 592.338 seconds. So let's say we'll convert this to minutes. That would be 9.87 minutes. So close to 10 minutes. It would take in the full-scale operation, not pilot plan, let's say the full-scale processing of the said solid, wherein you need to process half a ton, 500 kilograms of solid, which is containing 28% solid. It needs 10 minutes for you to reach this maximum concentration of 2.5. The saturation concentration of water is 2.5 kilograms per cubic meter. For this concentration to be reached for water with this volume of 100 cubic meter, you need 10 minutes of leaching process. Okay? Now, it has to be noted, and I missed to mention this, that in the process of the concentration here over a certain time, how will the concentration of the solution behave against the saturation concentration? So over time, your saturation concentration will exponentially decay. So this is exponential decay. So you see this exponential function. So there will be a corresponding decrease in the concentration of the solution over time as less and less amount of solute rather, gets to be leached out from the solid. So it's exponential decay. So this is the answer to our problem using the formula here provided by Paulson. The formula that allows you to determine the amount of solute in the solution at any particular time given its saturation value, its peak value, and all the other constants that should be stated in the problem. Otherwise, we can determine this set constant as a whole, just like what we did here. Now, that's in the case of the application of this formula. So let's go back to our slide. Okay, so this is our slide now. So we're using this formula to determine the time it would take a particular concentration value to be reached. Okay, that's your application. Now we go to sample problem from John Cooklis. So this time, I took a sample problem from John Cooklis, which is treated with, again, a graphical approach. But nonetheless, there has to be an application of the representations discussed in the slide regarding the N, the B, the X, and the Y. So we will use this sample problem. Now, in a single-stage leaching of soybean oil from flake soybeans with hexane, 100 kilograms of soybeans containing 28% oil is leached with 100 kilograms of fresh hexane solvent. The value of N for the slurry underflow is essentially constant at 1.5 kilogram insoluble solid per kilogram of solution retained. Now, calculate the amounts and the composition of the overflow B1 and the underflow slurry L1, leaving the page. If you have a copy of Jean Cooklis, this is an exact sample problem there, and it's treated with graphical approach. Now, we'll try, in this case, solving this purely analytical using material balance and the correct representation of the amounts stated in the problem. So I will stop sharing again here and we'll go to the board. There's the board. Okay, so I will just from time to time go back to the slide to get the information that we have. So in number 2, sample problem number 2, these are our given information. So we'll read the problem one statement at a time. So statement number 1, in a single stage leaching of soybean oil from flaked soybeans, so we take the oil from flaked soybeans, we use hexane, and 100 kilograms of soybeans containing 10 weight percent oil is leached with 100 kilograms of fresh hexane solvent. So how would we write this down? So 100, 100, and a 20% oil in this case. So we'll stop share. We'll go to my board again. Let me know if you cannot see my board. So you have this one. You have your LO here. You have your L1. You have your V2, and you have your V1. Just like the way we represent it in extraction. It says for LO that you have 100 kilograms of soybeans. These 100 kilograms of soybeans contain 20% oil. So I'd like to say that you have 20 kilograms of A in this case. And since this is 100 kilograms soybeans and you have already 20 kilograms A, or since it's 20 kilograms oil, 20% oil, then the rest of this 100 kilograms would be your B. So I'm writing now specifically the solute as A, which is our oil, and the B, which is our inert insoluble solid present in our original soybeans, which is our solid. Now, in this case, we're using pure hexane with the value of 100 kilograms. So this is pure hexane, and we will be having here, since this does not have any A, so we'll having here XA equal to 0. Okay? Now, the problem requires you to determine D1, L1, YA1, and XA1. The composition of the underflow, the slurry, and the overflow is being asked. So we will specifically focus on the A, since it's actually A that we're trying to account for in here. Okay? Now we go to our solution. So when you use material balance, in this case, remember again, class, you will only balance A and C. We don't balance the inert solid. So if we want to write, nonetheless, the concentration of B in the feed or in our solid, that would be NO, the concentration of the inert insoluble solid in the original solid feed. And that would be 80 kilograms of B divided by 20 kilograms of A. In this case, this would be a 4.0. Okay, that would be your NO. Now, if you use material balance, overall material balance, it's the same as the other separation process. You will have LO plus V2 equated to L1 plus V1, and this would also be your M, your bulk phase M. Now your LO has only to be in terms of A. We don't account for the inert solid B. So this would be 20. And your B is 100 because this is pure solvent. So we have L1 plus B1, and this is equal to 120. So you have an equation of L1 plus B1 equal to 120, which you can have L1 expressed in terms of B1. So let's say this is our equation 1. Remember, we need these two. Now, how do we determine L1? You have to look for a connection between LO and L1. And what is that connection? What is the connection between LO and L1? if I may ask. Since the problem is saying, by the way, I'd like to say, I'd like to read that part. I missed reading that. The value of n for the slurry underflow is essentially constant at 1.5 insoluble solid over kilogram of solution. What does this mean? This means that your n in this problem is constant with a value of 1.5 kilograms. That's the N in the slurry. So that would be 1.5 kilograms P over kilograms of solution. Okay? That's it. Now, again, I'll go back to my question. We want to find L1 and B1. How do we find L1 and B1 knowing that we have an equation which has two unknowns? So we have to look for a connection of any of these two with the given information provided here, this given information. That way I can find any of the two. That way I find the other one. If I find this, I'll find B1. If I'll find B1, I'll find this. But to give you a clue, your V1 is the last to be determined. Your L1 can be determined. How do we determine L1? How do we determine L1? Anybody? You have to look for a connection with L1 with the data that is provided here. We will just solve this using material balance. If you look into your book later, it's solved graphically. In our case, we solve it purely analytical, material balance. The key is finding a connection of L1 in the given information provided here. What should be that information? Okay, since we will be again, I will be buying some of your minutes again later on. So what you're going to do, you do solid balance. When you do solid balance class, you will have solid in feed. I'll just have it LO. Should be equal to solid in slurry. The underflow, that's L1. If we will account for solid in the feed and solid in the slurry, your formula would be the concentration of the solid in the feed times the value of the feed should be equal to the concentration of the inert solid in the slurry times the value of the slurry. So concentration of the solid in the feed times the value of the feed, concentration of the solid in the slurry times the value of the slurry. So we determined this already as 4.0 and we already have LO as equal to 20. Is that right? LO is 20 because it's only A that we're going to account for LO. And 4 is already determined here. It's 4. Then we have N1, which is stated in the problem, a constant of 1.5 kilograms B per kilogram solution. Then you have L1. In this case, you now find L1. So that's using solid balance. So you have 8 divided by 1.5. That should be 5.333 kilograms. So what do we have in L1? Kilograms, A and C. L1 is just A and C. LO is just A. Your slurry contains a solution having the solute and the solvent. It carries the same solution that is present in the overflow. So since we know already your L1, then we can find V1. So your V1 is your 120, and let's see, minus 5.33. That should be 100,
Miss.
yes,
4
14.
times 20, naguro, Miss. 80.
Ay,
Divided by 1.5.
so this should be 5.3. This should be
53 point.
53.
Yes, Miss.
Okay, kulang. So 53. And this should be 120 minus 53.3. That would be 66.7. Sorry. I-multiply ko lang yung 4 and 2. So this should be, we'll change this. Thank you. So this should be 53.33 and this should be 66.7. This is kilograms also, A and C. Right? But we have so far only answered the amounts of L1 and B1. The problem is asking also for the composition. How do we determine the composition? Sorry. How do we determine the composition? Anybody? How do we determine the composition of L1 and B1? Can this be determined using pure analytical procedure, or we don't have any choice, means we go to graphical approach? What do you think? So this
Pwede
one,
man, Miss, Miss?
yes, Kat?
Pwede, Miss, component balance.
Oh, it's okay. So since I'm seeing now my time, it's less than 1 minute and some of your classmates have already a class. So that would be something for you to check. How do we determine the composition of the slurry?